Welcome to Complex Analysis. Today, we are going to explore one of the most fascinating and mind-bending concepts in mathematics, the residue at infinity. We will learn how to measure the mathematical footprint of a function at the infinitely distant edges of the complex plane, and why this single calculation can sometimes reveal the secrets of the entire universe. Let us dive in. To understand the residue at infinity, imagine you are standing in a massive, endless flat field, which represents the complex plane. Scattered across this field are roaring campfires, representing singularities. A singularity is simply a point where a mathematical function breaks down, usually by dividing by zero. If you want to measure the heat from one specific campfire, you walk in a small circle around it and add up the temperature. This leftover value you measure is called a residue, and the act of walking that circle is a contour integral. But what if we want to know the total heat of all campfires? This brings us to a brilliant visualization tool called the Riemann sphere. Why does this matter? Because walking a massive circle around every single finite campfire would take forever. Instead, mathematicians visualize the flat, endless complex plane wrapped around a three-dimensional globe. The center of the flat plane sits at the south pole. As you stretch the infinitely far edges of the plane upwards, they all pinch together to meet at a single point at the very top, the north pole. Infinity is no longer a direction you travel in forever. It becomes a specific single destination at the top of this globe. Now that we have wrapped our plane around a globe, let us look at what happens to our contour integrals. In this diagram, you can see the flat complex plane at the bottom, with red dots representing finite singularities. The large blue circle on the flat plane grows outward to enclose all these finite singularities. As it grows infinitely large, it creeps up the sides of the Riemann sphere. Eventually, it becomes a tiny circle tightly wrapping around the North Pole, which represents infinity. Notice the arrows. Looking down from the North Pole, the arrows that were originally counterclockwise on the plane now appear to be moving clockwise. This orientation flip is crucial. To actually calculate what is happening at infinity, we need a mathematical trick to bring infinity back to a place we can easily reach. We do this by flipping the entire universe inside out using a simple substitution. We introduce a new variable, w, which is the exact reciprocal of our original variable z. Conceptually, this is the mathematical equivalent of teleporting from the infinitely distant edges of the flat plane straight to the center origin. As our original variable z grows infinitely large, our new variable w shrinks down to exactly 0. This means studying our function at infinity is perfectly identical to studying a modified version of our function at 0. Now that we have changed our variable, we also have to change how we measure our steps along the path. This means we must find the derivative of our relationship. Taking the derivative of w equals 1 over z gives us dz equals negative 1 over w squared dw. Here, dz represents a tiny step in our original plane, and dw represents a tiny step in our new flipped plane. The negative sign in front of the fraction is incredibly important for our physical understanding. It mathematically corrects the flip in orientation we saw on the Riemann sphere, ensuring we are still measuring our contour integral in the correct standard counterclockwise direction. By plugging our substitution and its derivative back into the standard definition of a residue, we get a concrete formula for the residue at infinity. Conceptually, to find what happens infinitely far away, we flip the universe inside out, multiply by a distortion factor, and measure the leftover value at the center. In this formula, R infinity stands for the residue at infinity. The symbol f is our original function. Notice we use z again here instead of w, simply out of convenience as a dummy variable. We replace every instance of the variable with its reciprocal, multiply by the negative reciprocal squared, and finally find the standard residue of this brand new expression at the origin. Before we calculate an example, we must introduce one of the most beautiful and powerful results in all of complex analysis, the sum of residues theorem. Why does this matter? Because it reveals that the entire extended complex plane is in perfect mathematical balance. A contour enclosing all finite singularities is mathematically identical to a contour enclosing infinity, just viewed from the opposite side. Since they are the exact same boundary but traversed in opposite directions, their total contributions perfectly cancel each other out. If a function has a positive mathematical footprint in the finite plane, it must have an exactly equal and opposite footprint at infinity to balance the universe. This brings us to the mathematical equation for the theorem. The summation symbol represents adding together the residues from all the normal, finite singularities scattered across the plane. The second term is our residue at infinity. The zero on the right side represents perfect balance. Conceptually, this theorem is an incredible shortcut. If a function has 50 finite singularities, you do not need to calculate 50 separate residues. You can just calculate the single residue at infinity and flip its sign. As one variable increases, the other must decrease to maintain that zero balance. Let us start with the simplest possible example to build our confidence. We are given the function f of z equals 1 over z, and we are asked to find its residue at infinity. We will use our inversion formula step by step. First, we substitute the reciprocal into the function to flip our perspective. Because our original function was already a fraction, taking the reciprocal of a reciprocal simply flips the variable back up to the numerator. The result is just the variable z itself. This completes the first step of shifting our perspective. Continuing with our calculation, we now multiply our flipped function by the required distortion factor. This accounts for the change in the size of our steps and the reversal of our circular path. We multiply negative 1 over z squared by z, which simplifies to negative 1 over z. Finally, we need to find the standard residue of this new expression at the origin. The standard residue is always just the number sitting on top of the single variable in the denominator. Here, the coefficient is negative 1. Physically, this balances the positive 1 residue at the origin, keeping the universe balanced at 0. For our second example, we will look at a slightly more complex function that has multiple singularities. We are given the function f of z equals to 2z over z squared minus 1. We want to find the residue at infinity and then verify our answer using the sum theorem. Our strategy remains exactly the same. We begin by carefully replacing every single instance of our variable with its reciprocal. This creates a complex fraction with fractions inside of fractions. While it looks messy, it is just basic algebra that we will clean up in the next step. Continuing our algebra, we need to clean up this expression by finding a common denominator for the bottom part. The denominator becomes 1 minus z squared all over z squared. By multiplying the top and bottom by the squared variable, we clear out the internal fractions. This leaves us with a much cleaner standard rational function, 2z over 1 minus z squared. This simplified function represents our original function viewed from the perspective of infinity. Now we are ready to apply the distortion factor. We now multiply our clean function by the negative squared reciprocal. This step is mandatory every single time we calculate a residue at infinity. We multiply the terms together and cancel out any common variables shared by the numerator and the denominator. After cancelling one copy of the variable z, we are left with this final expression, negative 2 over z times 1 minus z square. We are now ready to find the residue of this expression at the origin. To find the residue of this expression at the origin, we simply ignore the single variable z in the denominator and plug 0 into the rest of the expression. This is a standard technique for finding the residue of a simple pole. By plugging in 0, the denominator becomes 1 minus 0, which is just 1, and the numerator remains negative 2. Therefore, our residue at infinity is exactly negative 2. We have successfully found the mathematical footprint at infinity. Next, we will verify this result by calculating the finite residues and checking the sum. Now, let us verify this using the sum theorem. The original function has two finite singularities, where its denominator becomes 0. These occur at positive 1 and negative 1. We calculate the residue at the first finite singularity by multiplying by the problematic term, z minus 1, and taking the limit as z approaches 1. The terms cancel, and plugging in positive 1 gives us 2 divided by 2, which is exactly 1. This is the mathematical footprint of the first campfire in the finite plane. Now, we must check the second one. We repeat the exact same limit process for the second finite singularity at negative 1. The terms cancel again, and plugging in negative 1 gives us negative 2 divided by negative 2, which is also exactly 1. We now have all the pieces needed to test our grand theorem. We add the two finite residues together, which gives us positive 2. We then add our residue at infinity, which was negative 2. The grand total is exactly 0. The theorem holds perfectly true, proving our calculation was absolutely correct and the complex plane is balanced. To summarize, the residue at infinity is a powerful measure of a function's behavior at the infinitely distant edges of the complex plane. By using the Riemann sphere, we can treat infinity as a single, reachable point. We calculate this value by flipping the variable and multiplying by a distortion factor to correct the orientation. Most importantly, the sum of all finite residues plus the residue at infinity will always equal 0. This provides an incredible shortcut for solving complex integrals in physics and engineering. You have now mastered the residue at infinity. Excellent work!